Hello and welcome to the presentation of the tutorial Efficient and Flexible Implementation of Machine Learning for ASR and MT. My name is Rossenbach and I will give this presentation together with my colleagues Zeyer, Parnia Bahar and André Merboldt. The purpose of this tutorial is to give an overview of the existing deep learning frameworks for human language technology tasks. We want to discuss the core features of such frameworks in the context of sequence processing and discuss the application-oriented features in the context of different tasks such as machine translation or speech recognition. In general, we want to compare the needs of researchers to what are the requirements for production systems. All this will be done by using our internal framework Return as an example. We want to stress that this tutorial is not about how to design full pipelines for human language technology tasks, and it's also not about how to write complete return setups, but we will just use Return as an example framework. This tutorial should be interesting for active framework and toolkit contributors as well as general developers working on human language technology related software and of course researchers that are interested in flexible neuroarchitecture design. The prerequisite knowledge for this tutorial is being familiar with sequence tasks and human language technology in general, as well as having basic knowledge about deep learning frameworks such as TensorFlow or PyTorch. Also, it is nice if you have experience with designing and training neural networks. Because there are different terms used for deep learning software, such as platform, framework, library, API, or toolkit, we streamlined this a little bit in this tutorial, so we will always refer to any kind of software as framework here. The tutorial is split into two parts. So the first part is about the general implementation details of machine learning for sequence processing, and the second part will be about the specific model applications. So each of these two sessions will be roughly 70 minutes, and after that we will have a question and answer session each. So the first part, implementation of machine learning for sequence processing, will start with the frameworks overview. So here we will define the characteristics of deep learning frameworks for human language technology tasks and present a broad overview of the different existing frameworks and what their differences might be. Then we will have the presentation of my colleague Zeyer about the framework implementation itself. So here he will introduce our in-house framework Return and then discuss the core concepts of general machine learning frameworks and our framework Return. And this will be mostly about what are the requirements for sequence tasks and how can we find good solutions and implementations for this. The second part of the tutorial, the applications, will start with the presentation about machine translation by Parnia Bahar. Here we will discuss the recurrent attention models with attention expansions for the neural machine translation and talk about specific details on layer-wise pre-training, transformer networks, and hybrid MT. We then have the presentation about automatic speech recognition by André Merboldt. Here we will explain the different implementations for hybrid HMM models and end-to-end networks, as well as how to use an interface of our framework Return to C++ decoder Zeyer, and other details such as encoder pre-training or how to implement transducer models. After that, we have the language modeling. Here we will discuss in general how to have good implementations for LSTM and transformer language models, how to perform language model fusion in the context of ASR systems, and minor details such as sample softmax. Then, following up on the explanations on machine translation and ASR, we will discuss speech translation, where we will present a cascaded approach as well as end-to-end modeling. And here the focus will be on transfer learning and multitask learning. The final application is text-to-speech, and here we will speak about the Tacotron 2 architecture extended with global style tokens and using some attention extensions and vocoder integration as examples on what are the necessary features for frameworks. So now we will start with the first part of the tutorial by giving an overview of the different existing frameworks for sequence processing and introducing our framework Return. So for writing machine learning applications, there exist different deep learning backends, such as TensorFlow, PyTorch, or MXNet. And all these backends provide as core feature that you can have mathematical operations backed by hardware-optimized implementations. So they provide mathematical operations for CPU and for GPU, and they provide automatic gradient computation. So this is the key feature for neural network architectures. So those backends were extended by a large amount of new features. So nowadays we have neural network layer definitions, graph and parameter management, there are efficient data loading and processing pipelines, and there are plenty of loss and optimizer implementations. Also, because in some cases writing in the backend code itself was still a lot of work, different higher level frameworks were integrated into those backends. So for example, in TensorFlow, we now have the integrated Keras framework and the TensorFlow add-ons. And there exist additional wrappers such as Sonnet. For PyTorch, from the beginning, there was the torch.nn module to provide layer definitions, and there are additional wrappers such as Lightning or Ignite. And for MXNet, there is, for example, the more high-level Gluon API. So to give a more detailed definition of what we understand as high-level framework, so for us, a high-level framework provides some kind of model abstraction to simplify the code structure of your machine learning application. So these are abstractions for the model, but also for the data loading and for the training. The framework should provide predefined layer modules, which can also be quite complex. For example, as a self-attention layer. It should support multi-GPU or distributed training to be able to run your training on large data sets without waiting too long. And often higher level frameworks have an encapsulated training process with predefined parameters. So you just define your network and some hyperparameters, and then the training is basically a closed process. So the checkpoints are generated, there is automatic learning rate scheduling and other things. Frameworks that are designed specifically for human language technology tasks might have additional features. So those frameworks might provide specific data processing pipelines, such as spectrogram extraction for audio, or support codes or WordPiece models. They have predefined model architectures, so usually they have some definitions for encoder-decoder models, being based on LSTMs or the transformer. They often have example configurations for common tasks. So for ASR there is LibreSpeech, or for machine translation there are the WMT tasks. And also often you can download pre-trained models. So you just take a configuration, download a pre-trained model, and then you can perform recognition or translation on your user data. There are very many different human language technology targeted frameworks. So here we will only list a few of those. So there are different frameworks based on different backends. They have different highlighted features, and they also focus usually different applications. So all these frameworks have a different configuration flexibility, and some might provide more modular components, some have rather fixed architectures. And for some frameworks you might need internal code changes if you really want to implement a complete new architecture. And also some of these frameworks are more designed for a specific task, so changing the code to work with a new task might require a lot of work. So to go a little bit into details here, so giving some examples, we have open sequence to sequence Lingvo and Fersec that have extendable classes to have flexible model definitions, encoder, decoder definitions, or for data and losses. Open sequence to sequence, for example, provides a Python-style configuration file where you can easily update your hyperparameters and also have possible user code imports. In Lingvo, for example, everything is defined as a class, so even the task itself and the experiment design is in a class. So this provides some kind of flexibility. And Fersec, for example, provides having user folders where you can define your task or architectures independently of the internal Fersec code. So while these are maybe into different flavors of configuring different frameworks, there are some noticeable differences in the flexibility the different frameworks offer. So for example, we have frameworks that are more focused on specific implementations. Ref2Letter++ uses only a simple sequential text file to design sequence-to-sequence or CTC architectures and run speech recognition. And also SOC-A was originally only designed for 3 fixed neural machine translation architectures, so recurrent networks, convolutional networks, and transformer models. But for example, SOC-A was now also updated to be more flexible, and by introducing SOC-A 2, they switched to the Gluon API. Also, some frameworks might bring their own implementations. So Ref2Letter++ implements its own decoder, for example, in C++, which is said to have a huge impact on the decoding speed. And also Lingvo implements some custom C++ operations that are accessible via the general Python API to enhance the speed. So there are a lot of different pros and cons the different frameworks have, and in the following parts of the tutorials we will go into more details here. So now my colleague Albert Zeyer will take over and introduce our framework, Return.
Hello, now it's me, Albert Zeyer. So what is Return? Return stands for RWTH Extensible Training Framework for Universal Recurrent Neural Networks. All the code is published on GitHub. The framework is based on Python with TensorFlow and has lots of custom C++ and CUDA code. It can be used as both a framework and a standalone tool. Framework means you can import it. Similar are Keras, for example, or PyTorch Lightning. You can use that to write your own custom decoder, or embed it in server applications, have your own custom training loop, or embed it in some existing software, like our speech recognition tool called Razor. Or when you use it as a tool, you have main entry point, you provide a config. Similar are ESP.NET, OpenSec2Sec, FairSec, and many others. So you write a config and you run some given tool for many predefined but flexible tasks. This is still very flexible. You can define any arbitrary architectures or training schemes. So it's almost just as flexible as a framework. In general, Return is very generic, but some of our main applications are speech recognition for hybrid models. Then also we have encoder-decoder attention models for speech and translation and other end-to-end models, and also language models. The design goals of Return are high flexibility, simplicity, high training speed, and high decoding speed. The history of Return already started 2013 with a Cyano backend by Patrick Dutch and his student Paul Vogtländer. 2016 we got first TensorFlow support, and here we already introduced the data class, which will be very important. We will come to that. Then first paper, and here 2017 we got the building blocks for encoder-decoder attention models, including beam search, and these are very important. We will explain them. And then following from there, lots of people started to use it in our group, and we got a lot of further models all implemented based on this framework. The usage as a tool looks like that. You have this main entry point, you provide a config, maybe other options. You run this for training, forwarding, evaluation, beam search, or etc. The config format is either Python or also JSON extended with comments. The config basically defines anything, like the dataset, batching, the model. Importantly, the model is defined both for search or for training. And for training, it includes losses and regularization, and then also you define other training settings like optimizer and so on. In general, this is almost as flexible as the framework usage. So now to flexibility versus efficiency versus simplicity. These are features you want to have in a framework. Simplicity means that writing a config or code is very simple and straightforward. So this is for setting up the experiment or defining the model and so on. Then also you will get some problems usually when you write some new config. So debugging is also an important aspect, and this needs to be simple as well or straightforward. Then also another aspect is when you got some config from somewhere else, that reading this config is simple and straightforward. You understand directly what it does, what it defines. Flexibility is that you can define many different kinds of experiments or models. And efficiency is that the speed, both training and decoding, is fast. So basically all these items are important for research, but decoding speed especially is also is mainly important for production. To clarify a bit these concepts, in CUDA or C++, these are very flexible because you can basically write anything, but not so simple. Pure TensorFlow is a bit higher on the hierarchy. It's still very flexible, but still maybe not so simple, but simpler than C++ or CUDA directly. And but still it sometimes can get tricky to define something for optimal efficiency. ESPNet, for example, it's now very simple to use for what it supports, but now when you need to want to have some model which is not supported, then this again needs some extra effort. So what I want to say is all these features are trade-offs of each other, and in return we have a couple of new ideas to get the best trade-off. So now we come to the concepts of all kinds of frameworks. First of all, tensors. Tensors are ND arrays and generalization of a scalar, vector, or matrix. Tensor is the atomic unit of all modern machine learning frameworks. Example tensors are, for example, of these shapes. Any audio or any sequence, we usually would have these 3 dimensions: the batch dimension, time dimension, and feature dimension of type float32. So we say these are dense data. But the same data can be represented also with reordered axes, like time, batch, feature, so time first. This would be more efficient for recurrent neural networks, at least when you calculate it on GPUs or common hardware. Or then you could have 2 dimensions, batch time, for class indices, for example, for each frame. Then these are integers. We say these are sparse data. Or just batch, then class indices for the whole sequence, like speaker ID. Or when you have an image, it would have 4 dimensions. Batch with height, feature, also called channel in that case. Or the same data, the same image could be represented with batch and then feature at that second axis. This would be more efficient for convolutional neural networks. So some meta properties you have for tensor are shape, what axes are there, in what order, what are their dimensions. And these axes or dimensions have some identification or names, labels, like you have the batch dimension, but then you have the input sequence dimension, time dimension, or the output time dimension, or feature dimension. Then you can have sequences of different lengths inside your tensor. So important to note these sequence lengths which you have for input or targets, or when you have 2D data, image with height, the data type, float, int, string, and so on. You could have categorical data like class indices of integer. We say these are sparse, but you can reinterpret it as an one-hot vector of dense. So important here is that you also have an amount of classes. So we say this is a dimension. Or you can also have the class indices, the vocabulary, class vocabulary. So this concept of having named axes, named tensors, is already older. Here's some review. Don't go in detail through it. In return, 2016, we introduced this data class, which has similar ideas. Important to note is maybe 2019, there was this named tensors for PyTorch. And later, PyTorch officially adopted this idea and has official support for named tensors. Looks like that. Here you would define a 0 tensor of shape 2, 3, 2 dimensions, and you specify the names for these dimensions. N is a batch dimension, C channel dimension. So axes have names, usually just a string and explicitly specified, like here. Return data, it's similar but a bit different. They are predefined and have special meaning, like batch dimension. Also predefined by layers or implicit by layers. And this data object in return has much more other meta information as well. So, but coming to the axes and dimensions of this object. First of all, there are dynamic axes have sequence length, so we store the sequence length. Then the batch axis is kind of special handling for it. There are some defaults, like for time axis and feature dim axis. We have, for this dynamic axis, we have global unique tag, so it's a dimension tag object. It's not just a string. And usually there's no need to manually or explicitly define these dimension tags. First of all, by the data set, you get them automatically, they're predefined. For example, when you have an input x1 to t, this data x has this shape, batch, then time, and this has this dimension tag and feature. And the time here has this special dimension tag. Or targets, it looks similar, and here for y, 1 to n is the dimension tag. And then when you have other operations, like resizing operations, like pooling, rescaling, and so on, you would get new dimension tags automatically. Here, from pooling, you would get this new dimension tag. So some examples, this data input could look like that, 3 dimensions, batch time, feature. Targets, 2 dimensions, batch time. Importantly, now it's the D type, is changed integer. This is float, sparse, meaning these represents class indices. The dimension is the number of classes for this. And the vocabulary is also in here, and also a flag that denotes that these targets are only available during inference or decoding time. LSTM output would look like that, similar, but now time would be the first axis. Encoder usually is downsampled, so now the time is different dimension tag. Attention weights could look like that. Inside the decoder recurrent loop, you would have batch feature as the number of heads, and then the encoder time dimension. Or when you calculate these attention weights outside the recurrent loop, you would get an additional axis decoder frames, basically. And this is this axis here. So the data object in return contains multiple things. First of all, the TF tensor reference, and this is optional. So we can also use it without that, and then we say it's a template which just describes how the data looks like. Then it has a shape, of course, marking of special axes like batch, dimension, time, feature. Then it also stores the sequence lengths of all these dynamic length axes, like the time axis. It stores dimension tags, especially for the dynamic axis. It stores the data type, float, integer, or whatever TensorFlow supports. Then we have a flag called sparse. That means that then it's integers and the values are class indices. And we keep that as equivalent as the one hot vector in certain cases. Dimension, in case it's sparse, class indices, we also store the number of classes. It's an additional information which is useful to have in some cases. Also to have the vocabulary of classes. And then the flag, whether it's available at decoding or inference time. And also we store some beam information in it. We'll come to that. The data object, the usage of it, it's basically everywhere in return. It's a very crucial and important building block. Since the very beginning we had that for TensorFlow. All the layer inputs, outputs are data. Again, important to note, the most efficient tensor format depends on the operation. For example, when you have some audio, the standard format would be batch time feature, but for recurrent neural networks, it's more efficient to have time first. Similar for images, or when you use convolutional neural networks, it's more efficient when you have batch and then feature directly. So what layers do, they automatically convert your input to the most efficient format and then operate on that. If you want to do something like that, in other frameworks, it would be kind of difficult without such a concept of named tensors or data, or at least it's very easy to get wrong. For convolution, now just to give you some idea about this training efficiency, the difference between having the right tensor or wrong tensor, this is what all the common frameworks basically support, these two possible formats. If you use the right format, you get 2.5 times faster approximately. Now to a new concept, layers. Most neural network literature and also frameworks have this concept where a layer encapsulates some common operations. In PyTorch, this is also called modules. And some basic layers are very similar in all these frameworks. Dense, linear layer, convolution is the same. So the whole neural network or model is defined by interconnecting these layers. One example here for a linear layer can have optional nonlinear activation function also. You have some input for a layer, some output, then some parameters which can be trained. Then it does some operation. Here matrix multiplication, bias and so on. And you configure it in some way. So the activation function, the output dimension, input dimension as well, but although this can be implicitly derived from the input. Optionally, you usually can define what's the parameter initialization, regularization, extra losses. So a bit more about layers in frameworks. They are usually of different complexity. For example, they are low-level layers, very atomic. You have directly the activation functions, for example, reload, return age, then direct wrappers for common TensorFlow functions, reduce min, or constant layers, TF constant, variable layer, TF variable. Dot layer is just TF metmul, two inputs here. So to note a bit the difference between TF metmul versus dot layer in return, this is a bit different like in other frameworks, PyTorch, or where you would directly call these, so there's maybe not the need to have special layers wrapping these. But in return, as we have this data, it adds some more logic to it, which makes it actually simpler and more powerful. So because now we can specify using data which axis we want to reduce in this matrix multiplication. So it becomes more like einsum with named axes. So this becomes much nicer and more elegant to do matrix multiplication. Then you also have higher level layers, like linear layers, only slightly higher level, but still more than these. You have matrix multiplication, but then also addition, parameters, activation function. Dropout is a bit more than that also, batch norm layer. And then self-attention layer, it's again slightly more complex, but you can even have the whole LSTM as one layer, or the whole transformer as one layer inside your framework. So there are some problems with these higher level layers in a framework. First of all, details can be hidden. And so the users often don't really know all the details. And this might be a problem or not, depending on the use case. There are lots of variations, of course. LSTM or transformer. First of all, for when it's older, like an LSTM, then it's mostly settled. So there's some standard variant, and you would probably use that, and this is not too much a problem. But when the model is more under active research, like transformer, this will likely change in the future, and further options and variations will be added, and this can become messy. So a framework could only support a standard variant, then it's kind of clean and only has few config options, or also the framework could have lots of options. But in any case, often it's not exactly the variant you want. So now when you think about how to do research on new variations of transformer, for example, what you could do is you could add some new further options to an existing layer. But this can become quite messy. And then you could edit internal framework code, but then you enter with your own fork, and you might diverge from main framework code, so cannot easily collaborate anymore. It's a problem. Or you can copy it or re-implement it and add some new custom layer. Okay, but then this might add extra effort later on. So when should you adopt this in the framework? How? Or if at all? And then if it ends up in the framework, you end up with lots of options in the end, or lots of variations. And many of these options and or variations will not be used in the future anymore. And then the framework becomes complex and bloated, and lots of rotten code because it's not used anymore. And then it's unmaintained. So this is kind of bad. So we want to avoid that. So in return, the layer conventions to avoid this is layer should be generic and reusable in many different contexts to avoid rotten code. It should be simple functionality. Only apply single function, atomic, ideally. Of course, that's not always the case. So this is to avoid layers which become more and more complex over time. There are some exceptions, like very common functions are combined. Linear layer is already combination of multiple things, or we even have a layer for LSTM. And of course, this all grows historically, so there are some bad examples. One maybe here to note only is a self-attention layer, which is not quite nice in the end. We will come to that a bit more. A layer should be flexible on the input. For example, a linear layer supports any kind of shape. It could really be anything. It could be multiple sources and it would concatenate in a feature dimension. Could be sparse, meaning class indices. In that case, it would be a lookup or embedding. Here, important to note, number of classes are needed here to define the dimension. And it gets it from data. Or when it's dense, then it's a matrix multiplication. The layer can automatically transform the input when it's more efficient. Like a recurrent layer would transform to batch to time major. And the layer is used to define it for both training and recognition, including beam search. Some comparison between some frameworks, like to use transformer in Lingo or FAIRSEC. The base model is often implemented inside the toolkit code. So the user code would often derive from some existing base class, and often there are multiple inheritances in the end. So to really understand the details, you would need to follow the whole class inheritance and read the framework code. We argue that deriving from base classes makes actually quite hard to follow really what's happening in there. ESP.NET, again, the models are implemented directly in the toolkit code. So in the configs, it looks very simple. You just write something like encoder as a transformer. So this is very simple for supporting models. But now when you want to have some modification of transformer, it means that you need to edit the framework code. And also to understand all the details, like what variant of the transformer is that. You need to read through the framework code. In return, the approach is a bit different. Basically, the idea is that you define the whole model inside your config. There's no derivation of some base models. The result is that the config gets quite verbose. Details become directly clear from just looking at the config. And that's for the model itself, for training and for recognition. So no need to look at internal framework code or documentation. Ideally, of course, it's maybe not always the case, although we really have mostly this covered. And most layers are well tested and often used because they're atomic, and in basically all your models you always have the same atomic building blocks. Also no rotten code. Of course, ideally, there are bad examples. So a bit technically to the layer definition. So first of all, there's some API to resolve layer dependencies, and importantly, layer dependency can also be optionally only used at decoding time. And this allows for automatic optimization later on. We will later show this in detail. Or the layer has an API to get just the data template, so without TF tensor. So we will use that, for example, in recurrency. And then, of course, the layer also defines what actually is the calculation. And then it gets out the data with TF tensor. Optionally, also, layer can have parameters, can have losses, constraints, can have other sublayers, and can have hidden state when it's inside the rec layer. Okay, now to the network topology, this concept. On the example on return, here it's a two-layer BLSTM model. First layer forward is the LSTM here, backwards here, gets the input from data, that's the input data. Second layer is here, and here it concatenates forward and backward together. And then the output concatenates the last LSTM layer, like that. This defines the model for decoding and for training. Another example, convolution layer first, and then two unidirectional LSTM layer and output. So that how does it work? It looks for an output layer first, also for layers with losses. Then it looks the class. This defines what type of layer this is. Here it's a softmax layer. Then it will resolve dependencies, here the from, and recursively constructs them as well. And that's basically it. Then it constructs the layer itself. Okay, now next important aspects, the data set. This concept, of course, you need to have some data. For training, you would have supervised data input-output pairs, or for unsupervised training or self-supervised training, just some input, like text to train language model. And then there could be additional information data, like for speech, the speaker ID. A generic interface to generalize from that is to have multiple data streams. In TensorFlow, this is called feature columns, a similar idea. And these are of different types or formats. Also important, not all of these data streams are available at the decoding time. Another aspect here related is preprocessing and feature extraction. It can be part of the dataset, or you could have that as an external part. Also related is the mini-batch preparation logic. So first of all, you would want to have some shuffling of your data. Then you can take the whole sequences, or you can take chunks of sequences, depending on your type of training. You have padding, which you want to try to minimize, and there's some special logic for that. A remark, when you have reinforcement learning, it looks slightly different from this concept. You have an interactive environment, and it gets a bit more involved. So in frameworks, but the standard dataset in frameworks looks very similar nowadays. TensorFlow has this dataset, PyTorch has this dataset, Return also has a dataset. And they all look quite similar. You have data streams. Then you have some API to get the next utterance. Now a bit special about Return is that we also have an end of epoch signal, which we can get here, and some API to initialize a new epoch. And also sorting, shuffling per epoch. So this is kind of extra in Return. In Return now, this is very similar in also other frameworks. It looks like that. You have a couple of existing implementations, external sprint dataset like an interface or a speech recognition toolkit, or HDF, or some OGG zip format, or some special corpora datasets for existing corpora LibreSpeech. Then there's something like metadataset, which can be used to combine other datasets, and then a couple of datasets which create artificial data on the fly, which is very useful for debugging or playing around with some new model. When you have new corpora now, your possible options is to convert it in some way to some of these existing datasets, or you could write your own dataset implementation, which is kind of simple also. All of that is very simple, similar in other frameworks as well. The next concept is the training execution guide, as just as an example. It also looks very similar in most frameworks. You have setup in the beginning, construct your network for training, then losses, gradients, you initialize the parameters, maybe load some checkpoint, then you train an epoch, cross-validation, then you learning rate schedule update, and save the checkpoint and repeat with next epoch. Of course, there are some variations to that. For example, some toolkits don't really have this concept of epochs, but just counts the total number of training steps. Also, you could have some more complex training loop. For example, generative adversarial networks, you would have multiple decoupled losses. Or when you have reinforcement learning, it's a bit more complex. You have this rollouts and a replay buffer. Okay, now to another important aspect, decoding or beam search. First of all, why do you need some special logic for decoding? When you think of image object recognition, it's not so clear. You would just use argmax and it's done. But when you have a sequence task like speech recognition, then search space is too big, because now you search for sequences. So usually you would need some pruning in your search process, and you would have a beam search algorithm. So on beam search in frameworks, first of all, beam search could just be external. So in Return, for example, we have interfaces on multiple levels to make it easy to embed it in other frameworks or toolkits, like our speech recognition toolkit. Or the framework can directly support beam search, and many frameworks do that now, Return, ESP, like Lingo, and many others, basically all which support end-to-end models, because for end-to-end models, it's just reasonably simple to do beam search. The beam search could be generic, so meaning that you could have multiple stochastic or maybe latent variables to search over in any custom way. Return supports that. It has basically supports any number of stochastic variables, any dependency graph. This is kind of a unique feature because in most other frameworks you have one single hard-coded stochastic variable for just the output, no latent variable. Then also the question is, how do you define the model or the code, the logic for training versus decoding? And return is also special here. It has, you define it in your config, you have a single definition which is used for both training and decoding beam search. And this is a unique feature as well. And we will demonstrate how this is even possible. In most other frameworks, at some point, you have a separation of the implementation for training versus decoding. And this can be suboptimal. This means you first of all need some of the code needs duplication, and this can lead to inconsistencies. Okay, now to recurrency. Recurrency in return specifically means basically very generically any step-by-step execution where the current step depends on the previous step. So that can be used to define a recurrent network or an LSTM, but that can also be used to define a beam search or any kind of dynamic programming calculation, like a forced alignment. So a very generic concept. So in return, we have this rec layer for that. So first of all, it supports some predefined units like an LSTM, and for those we can use our very efficient native implementations. We will come to that later. But most importantly, these can be used to define any possible recurrent formula. And then the subnetwork which describe the calculation frame by frame. So it's a very generic wrapper around TF while loop. While loop means that you run some body iteratively while some good condition is true. In return, in the subnetwork, it looks like that. This special syntax pref layer is used to access the layer, the output from the previous frame. So this can be used now. Here's an example to define an LSTM in an explicit way. So it's very straightforward, everything here. Here I highlighted the access to the previous frame. So here the input is the previous output concatenated to the data source. And here the previous C is the previous sale state from the previous frame. And it's very straightforward. So and this is what we will discuss mostly here. So when you have that, you can do some automatic optimizations, like layers which are independent from this recurrent loop can be moved or calculated outside of the loop. This is very important, and we will show that. Beam search then also can be implemented that way. This is to manage stochastic latent variables. So beam search, first of all. An example for simple encoder-decoder model without attention. Here's the encoder and last state, and then the decoder is this what we call output layer here, and here is the subnetwork, and here is a choice layer. A choice layer gets an input from a probability distribution, this P, that's the softmax here, and operates in some classes. So the choice layer represents some stochastic optional latent variable. There are two modes which you can have. You can have search flag enabled. That means now this choice layer would select the n best via top k from the probability distribution. And you get some beam. And we hide this beam internally in the batch dimension. So we have some modified batch dimension. So all other layers basically don't really know about beam. Here they just operate as usual. So the output shape is batch, modified batch, and integer because you have class indices. So then when you have now search disabled, which is the default in training, this layer would return the ground truth labels, which you have given in training. So the output shape is batch and integer classes. So the same as before. I mean, different batch now, but it's the same format. And importantly, you don't have the dependency on P, on the probability distribution in that case, because you just use the ground truth label. So then you don't have any dependencies anymore on the layer. And this will be important for the automatic optimization. So a bit on the internal is is a search choices object which stores the scores on its current hypothesis. It references to the layer. It has this where it comes from, the source beams. Here you can look these functions to understand a bit how it works. So the rec layer remembers all these source beams with the class indices and final beam scores, and then at the end it would do an inverse while loop to backtrack the final hypothesis. Now to the automatic optimization. So when you construct the network, we have something like the mode flags. These can be that you are in training or that you want to do beam search. And the computation graph depends on these flags. For example, dropout would only be used in training. Most importantly, especially in the rect layer, some layer dependencies depend on mode flags. We already mentioned this pref output or the output. These are the ground truth labels in training. So there are no dependencies to get this output. In decoding, you would predict it. So then you would have the dependencies. So this can have a huge effect when it does not have dependencies anymore. Also, transformer can be defined in a similar way and then does not have any dependencies anymore. And that is how the transformer ends up in the fully parallel training, the automatic optimization. Here again, the same example from before. In this example, so output is independent of anything, so it's optimized. But then also the embedding here can be calculated independent from the loop. And then also this LSTM here can also be calculated independently. And then this efficient implementation, native LSTM2 here, can make it very efficient to operate. Then P in the end also operates independently of the loop. So basically there's nothing in the loop anymore. All of this has then very efficient implementations. To give some example numbers, with the optimization you end up with 8 seconds per epoch, without 14 seconds. So it gets much faster because of automatic optimization. So when you now defined your model in the config, so how would it look like? First of all, you would define it in a way as it's used for decoding time, using the stochastic variable. But this is a single definition, which would also be used at training time. So you would define it in kind of autoregressive model to predict the next label, given a history. And the choice layer is a crucial part here. So again, to highlight, there's no separate logic or code in your user definition or config model for training versus decoding. If you would need separate logic, that's training versus decoding, so that would be more efficient effort for you, the user. Also, separate logic can lead to bugs or inconsistencies between training versus decoding. So that's why this is an important feature to have. But also important when you have this is the automatic optimization to make it efficient for the choice layer. Teacher forcing basically means this previous layer is given by ground truth. So this still makes it as efficient as possible. So some example for encoder-decoder attention, encoder-decoder. We don't go through all of that in detail now, but important to notice that it's very straightforward in return to define how the calculation looks like, based basically on the mathematical formulas you are given, including the latent variable. So it's output here, predictions, decoder state, and attention. So to explain the automatic optimization on this example, in training, what would be optimized? First of all, the input layers. These are as input for the loop. First of all, the output is given as ground truth targets. Then the embedding is also given. Encoder context, of course. We defined it internally of the loop, but this can be calculated offline. In the loop, you still have this LSTM and the energy calculation and the attention calculation. So all of this stays inside the loop for this specific model at least. Then output layers, after you calculate the loop, is the readout in, then readout, and finally the output probabilities, softmax. Also the loss then is based on the output, would be calculated on the whole sequences at once. So this is much faster then. In decoding, it looks differently. Now the input layers moved out, still the encoder, this can be calculated offline, but otherwise everything now is inside the loop, because the output depends on the output probabilities. And also the end flag is now used to signal the end of the sequence. So nothing otherwise is moved out. Another example, there's some model like the decoupled decoder LSTM, proposed multiple times. This simplifies a bit the LSTM inside the decoder. It removes the input of the attention. So in return to modify that, you would just remove this part here, and otherwise you don't need to do anything. And now the automatic optimization would make this very much more efficient, because now there are no the attention don't the LSTM doesn't need have this dependencies, this recursive dependency anymore. And so just removing that would make it much more efficient. Transformer is a more extreme example. Again, remember, you define the model like you would use it at decoding time, including a choice layer. And now the automatic optimization would move all layers out of the loop, and you have very efficient training. Basically, this results in the standard training recipe now for transformer. But you defined it in a way which is used both for training and decoding. Another aspect is something like sequence training, minimum expected risk training. Before, the choice layer in training returned to the ground truth, but you can, of course, have this flexible. You can also use beam search during training to implement something like this. This simple and flexible way to implement all kinds of variants like minimum expected word array training, maximum expected blur training, also optimal completion distillation, and so on, scheduled sampling. Here's an example for minimum expected word array training. You have the output, the decoder as before, but you would enable search for this layer during training. So the output here is a beam basically with multiple hypotheses. And then the loss is defined like that. You would get from output this multiple hypotheses, and you say, okay, you want to calculate the expected loss using some other loss, here's the edit distance, and the scores of the beam represent the probabilities of each of the hypotheses. So this would define the expected loss. And that's it. Now it would calculate the expected loss. Another very important aspect, I already mentioned you define stochastic variables, but you can also define multiple stochastic variables. For example, when you have a model like hard attention, segmental model, you would introduce a new stochastic latent variable, t. So kind of standard way would be to introduce it here, and then as a product over the labels looks like that. And now you split it up, the probabilities, into two parts. This is probability for the output as before, and here's the probability for the t, the newly introduced stochastic variable. An approximation is that the sum can be replaced by maximum. So when you have that model, what the common tasks are to calculate forced alignment, you keep this y fixed, the output fixed, and search over the t, the latent variable, the hidden variable. Or you can do research over both y and t. And in return, this becomes very simple again with the choice layer. You use choice layer as before for y, and you add a new second choice layer for t. And on the hard attention model, this can look like that. Here's the previous frame, and that's the current frame, label frame. So you have two stochastic variables, t and y. First to note is dependencies on these stochastic variables looks like that. First this t from previous frame, then y, then t from current frame, and y from current frame. This is the way to denote it in return, pref t, pref y. First, thing to note is these are different beams, meaning when you do top K selection here, it's a different selection from compared to here. And here again, you have different top K. So that's what we say are different beams. You have 5 different beams. First of all, no beam, that's from the encoder. And then these 4 different, pref T, pref Y, and so on. And now when you think the input, for example, for this LSTM here, has the input from different beams, pref T and pref Y here. You need some way to combine these beams. And how does return do that? It looks which is the latest beam, pref Y here, and then it transforms this pref T beam automatically to pref Y beam, and then it can be combined. And that's for every layer here. Here, again, pref T and pref Y would be combined. Here still again you have pref Y. Here you do a new choice, get a new beam. So now here you combine no beam basically together with a T beam, and you would end up with a T beam. Here you combine T and pref Y, and you end up with T beam. So here you calculate the probability distribution for Y, and now you have here get the Y beam. In return, when you want to look that up, that's all this translate to common search beam function. Okay, coming to training. First of all, training means always to minimize some loss, and this can be defined in return inside of the network or attached to a layer based on the layer output. This would not be used at decoding time. There are some predefined losses, cross-entropy, minimum expected word error training, many others. You can have as many losses as you want and loss scales, and you can also define any custom calculation as loss, and the layer output itself is loss. Of course, regularization, optimizer, like gradient descent, it's important for training, scheduling, learning rate deregularization, and also pre-training in many variants. Pre-training in return means also, again, you have some loss, can also be supervised or unsupervised, can be different loss than you would do in the standard training. You can have different network topologies for each epoch. So you can start with one layer and add more and more layers. You can then it would automatically copy over the parameters from one epoch to the next as far as possible. And this is, of course, configurable, and new weights or layers you add are then randomly initialized, or you can also configure that. Also, you can increase the dimension. So when the dimension increases, you would still copy over existing weights, and the other remaining weights are randomly initialized. Some generalization of that is we have some custom Python function you can define in a config, and you can override really any kind of stuff in this function for each epoch, like loss or hyperparameters, like batch size and so on. Freeze also some of the parameters. Then we generalize it even further to a custom training pipeline, can be seen as a generalization of pre-training. For example, you can have this training pipeline to train a small neural network using frame-wise cross-entropy with a linear alignment, and then calculate a new alignment. And then train it again on a neural network using cross-entropy with a new alignment, and repeat that process with a new alignment to realign. Or another example, you could, for example, use CTC model with CTC loss, train that, calculate an alignment. Then you can train a more powerful model like transducer and use cross-entropy with new alignment. All of that is kind of possible to specify in one single config in return. Regularization is very standard. You have extra losses, layer 2, other auxiliary losses or model variations like dropout and other things, or data augmentation and spec augment. These are just extra layers on input and only be used in training. Or also you can configure that in any way you want. So this is all in the same config. For multi-GPU training, this is really another important aspect of the framework. In return, we have now 3 different implementations: custom engine for Cyano. Then in TensorFlow, we use Terawatt, or also we support distributed TensorFlow. Here, a lot of stuff is already given for you by TensorFlow. Dataset distribution can be charted or different random seeds. The parameter reduction can you can sum all the gradients, so synchronized. or you can average the parameters after n steps, so it runs more asynchronous, or you can average after some time, which makes it possible to mix even different kind of hardware with different speed. Okay, now to native operations. First of all, motivation. First, why do we want that? Speed up, of course. LSTMs or CTC loss is common in calculation to speed up. So why would it be suboptimal to write it into pure TensorFlow? Why is that not enough? That's not really clear why that is actually. So first of all, most TensorFlow operations would create a copy of the tensor. Even simple operations where you would not expect it, like split operation. To note here, this is not a memory problem because tensors would get freed if it's not used further, but this becomes a performance problem because you need to go through the whole tensor each time, every single op. Then the gradient might be suboptimal. First of all, it might require too much memory because it usually remembers everything from the forward pass, which is neat. There's some solution to that, like automatic gradient checkpointing, but it's not used by default in TensorFlow. Also, there's no automatic optimization here. So this can be solved by when you customly define your own gradient, but this would be more effort, of course. Memory can be distributed on the GPU. Especially when you have a loop, then you would get a separate tensor for every single iteration. So then it's very much distributed. And this is very inefficient. It's much better when you have one consecutive contiguous block of memory. There's also some overhead by the individual TensorFlow operations. Although this is really minor compared to these others. And also TensorFlow would automatically compile it when you enable XLA. So solution is write native code. Why is it faster? Again, first of all, most importantly, it can operate in place on tensors. This solves most of the problems we mentioned. No other unnecessary copies are needed. Also, you can operate on one consecutive block of memory. It forces you also to write a custom gradient, which then also makes it faster. I mean, more effort, of course, but yeah. Problems can be difficult. Memory unsafe, needs more debugging. Also need multiple implementations. Both on CPU and on GPU usually would have a separate implementation. So our approach in return is we have some wrappers and helper code to simplify that first of all. And most importantly, we have an abstraction to allow to write single code which is used for both CPU and GPU. How do we do that? You write the kernel in CUDA style using standard CUDA elements, thread index, block index. You write it in a way that it's flexible with the amount of threads. So for example, this is an LSTM. This is really our code of an LSTM. And on CPU, it would have some wrappers for CUDA, and it would define all these CUDA concepts, grid dim, block dim, and so on. So that way, it would use the same code also on CPU. And this results in our native op framework. Already had that for Cyano, then later ported to TensorFlow. And this is also easy to port to other frameworks like PyTorch. So the history a bit, initially we had the CUDA implementation by Paul Vogtländer for Cyano. Then we introduced this framework. Then I ported this initial CUDA implementation to this framework. Then we had TensorFlow implementation of that. And later also new implementation of the LSTM, which got a bit faster and even more flexible. There are multiple implementations you can use after all in your framework, any framework, but especially return. It's the standard TensorFlow official LSTM cell. There was also this block cell. Then the CUDA and LSTM, of course, and our natives. Cell versus fused means cell runs on a single time step, while fused runs on the whole sequences, like cuDNN does that as well. To compare now, our native was pure DNN versus LSTM block versus pure TensorFlow. Interestingly, our native is the fastest in both cases. On GPU, it's very similar though to cuDNN, but cuDNN does not exist on CPU. And on CPU especially, ours is also the fastest. So this is a very nice result. And native LSTM2 is even faster than that. So now to conclusion. How do we get flexibility, simplicity, and efficiency? In return, important features for that. First of all, this data object together with dimension tags. This made, first of all, simpler to read and write code, simpler also for debugging. Also faster, because now some of the layers really make use of most efficient tensor format. Then this generic rec layer and choice layer to define any autoregressive model. Or any model which can be defined in an iterative way. This is both very flexible, because basically anything can be described that way, and also simple. And this is used for everything, like including beam search. So importantly, you have one single config for beam search, forwarding, and training, single model definition. This makes it, first of all, simpler to read and write code. Also leads less debugging, because there are no inconsistencies between your beam search and your training. And then automatic optimization is there to make this efficient, especially this aspect of the single definition, but also makes it more efficient in some other cases. And again, this makes it more simple to read and write, because you need less tricks to make it efficient. And finally, the native op is also very efficient, very important for efficiency. It's basically 6 times faster than standard TensorFlow. Of course, we had some negative experience in turn historically. So, because many aspects have historically grown, it leads to some strange and inconsistent APIs. Also, we try to keep backward compatibility to older setups. And that means that we need to rely on strange behavior in some edge cases. And we must keep these behavior to keep compatible. And we have lots of test cases to ensure that everything works. But this is, of course, also a good thing that we have that. When we introduced the TensorFlow backend, we kind of did it in a new way. We did not really have the intention to keep Zeyer and TensorFlow compatible, to allow for some new ideas. To keep compatible with the old setup, though, we introduced a flag use TensorFlow too. So it means for TensorFlow, you needed to rewrite your configs when you wanted to use that flag. But this enabled to use new ideas, but still keep compatible. So this can be helpful sometimes to introduce some new interface or backend. Data, of course, is very useful to have in return, but also the features have historically grown. For example, dimension tags were introduced later. We already distinguished them before, especially for attention models. You need to do that, but it was a bit more heuristically. Beam information also was added later. We also had that before, but that kind of got cleaned up later on. There are some design choices which turned out not to be so useful. We distinguished between shape without batch dimension and then batch shape with batch dimension. Constructor is a bit unintuitive. But again, these are complaints on high level. It's a very important feature after all. Dataset API, it also was historically derived from a single dataset. There were no multiple dataset. And then generalized from that. And when you do that, it grows kind of in a non-controllable way, kind of. So it's not so well defined in all cases, and this leads to inconsistencies. But again, after all, having some API like dataset turned out very useful. Also, this dataset is more powerful than in TensorFlow, so it's still more generic than that. This automatic data inference, when you have, especially in a recurrent layer, you can define it here. The output depends on this A, and this A depends on pref B, so B, and B depends on A, so you have circular dependencies. So features dimension are clear in this example, but what's not clear is what is the axes or dimensions. It could have another dimension which is not specified here, or what's the data type. This is mostly resolved nowadays because we have some reasonable default which make exactly this example here would work and would behave like maybe you would expect it. It would use float 32, not integer or so. and there would be no other access, which is maybe the thing what you would expect. Self-attention layer is another example. This has become too specific. For example, our current options are all these here. That are too many, at least in my taste, and still it's not generic enough. People want to add more for the special need. And also some of them, or most of them, are maybe not so obvious. These first three are maybe obvious, but all the others maybe not so much. And this is bad. This is something which we wanted to avoid. So this is an example when you would use these, you would need to look at the documentation or the code to understand really what's happening there. A solution to that is to split it up into more atomic building blocks. So some future plans and ideas is first some new syntax I have in mind to introduce, more like PyTorch or Keras, instead of defining this dictionary. This is just syntactic after all, but it would maybe be more familiar, and also you can have your IDE used for auto-completion. And that way you now define a new kind of interface to defining a model and so on, and by that you can introduce more clean behavior. You can clean up a bit of the messiness which we have. Another aspect is to have some concept to reuse common parts, like transform or as backlogment. For example, you can introduce a concept where you import from some JIT repository some code, like we have our return experiments repository with many of these already defined. Then more support for return as a framework to use it more in a way like you would use PyTorch or Keras. And also reinforcement learning. For that we already support most things, but you would maybe add a few extra features for more interactive environment, so extended data set. Replay buffer, so here you would have some generic auxiliary database. That's an extension of what we have already.
Hello and welcome to the second part of the tutorial, Efficient and Flexible Implementation of Machine Learning for ASR and MT. My name is Parnia Bahar and this is a joint work with my colleagues Zeyer, Nick Rossenbach, André Merboldt and Dr. Ralf Schlüter. The second part of the tutorial reserves for the specific models and applications. After getting the fundamental knowledge about return as an exemplary case to consider machine learning implementations for sequence processing and classification in the first part of the tutorial, in the second part, we would like to discuss application-oriented features in the context of machine translation, automatic speech recognition, language modeling, speech-to-text translation, and text-to-speech. We bring some examples of different models and we show the ease of their configuration. Our main focus is on return or framework, however, we compare to other frameworks as well. Let's start with machine translation or MT. Machine translation is a task of translating text from one natural language into another, for example, from French to English. As you may know, the current state-of-the-art models are based on neural networks, especially encoder-decoder attention architectures, in which the encoder and decoder can be composed of different networks like RNNs, self-attention, convolution, combination of these networks as well. After the era of phrase-based system to neural-based approaches in the production system, there are plenty of frameworks that offer neural machine translation, such as Tensor to Tensor, SoCai, FairSec, OpenNMT, and many others. They all offer many features to build a strong state-of-the-art model for machine translation, and even some of them provide pre-trained models with data pipeline for fast verification. But in general, what MT requires from a framework? Besides the general features like flexibility, simplicity, scalability, and extensibility as mentioned before, we would like to easily set up our architecture to enable different models. Recurrent, convolution, transformer. We want to have different combination of those, different attention mechanism, as well as data pipeline, pre-processing and post-processing. How about model units, fine-tuning? It would be nice to have attention visualization for better explainability, especially for the transformer architecture. Generating synthetic data in low resource scenario, and some general features as well. In the following slides, I am going to discuss some features proven to be important for machine translation, with the main focus on our framework Return as an exemplary framework to implement machine learning methods for sequence modeling. And the first model is the recurrent attention model. As the name suggests, the recurrent units are the main component of this architecture. In the encoder, we have bidirectional LSTM, H of J, and in the decoder, we have a unidirectional LSTM, S of I. Then an attention function measures the similarity between H of J and S of I to get some scores. We normalize these scores to obtain attention weights, and given these attention weights, we compute a weighted sum of encoder representation, or known as context vector. In the decoder, we have two dependencies, therefore two implementation. In the first version, we first compute the current target word using the previous decoder states, and given E of I, we update our decoder representations. While in the second version, we first update S of I using EI-1, and then given S of I, we predict the target word. You better include Si-1 in the second version to compute your attention computation, because Si-1 does not include it explicitly. But why I'm highlighting this fact here? Because in many frameworks, one of these versions has been already implemented, and if you want to switch between these two, you need to go to the code and correspondingly change some parts. But as explained in the first part of the tutorial, you can construct the whole network in a configuration file in Return. And here you can see an example of recurrent attention model and its configuration. The first part corresponds to the encoder, like forward and backward LSTM. Then we have a rec layer representing our decoder. This part of the config corresponds to attention mechanism. Given previous decoder state and encoder representation, we compute the score. We multiply it with tangent hyperbolic, then we transform it to the scalar value, then we normalize it to get the attention weights. And as you can see here, this is the first version where we first use the previous decoder states to compute the readout layer as an input to the softmax to predict the output word, and then given the output word, we update our decoder state. But how about the second version? You can simply have the second version in Return. As you can see here, you need to change a few layers in Return. Here, as you can see, we first update the decoder state using previous target word, and then given S, we predict output word. How about attention extensions? For example, if we want to have some past alignments as coverage information. For example, here we have fertility concept with the maximum fertility value of 2 as formulated here, and what we can do, we can use an eval layer to accumulate the attention weights first and then multiply it with the fertility value. Given that, then we can include it as a third term in our attention computation. We can also equip our attention computation with the previous context vector. First, we get the previous context vector, Ci-1. Using a linear transformation, we transform it, and then we add it as a third term in our attention computation. It can be also included in the LSTM computations. Besides C of I, we have Ci-1, and as you can see here, it is included. Also, we can have other attention types like multiplicative. Therefore, we need to use the dot class for that, and the rest of the network will remain the same. We can have multi-head additive attention instead of single head. To do so, both a split dimension layer and merged dimension layer should be used. First, we need to divide the encoder representation by number of heads. Let's assume H is the number of attention heads in the encoder. F represents the feature axis here. And then in the decoder, we need to merge them again to flatten to the final dimension. If we want to do attention extension in other frameworks, for example, Sokai NMT offers some features via options. For example, we have RNN attention type to specify which attention component we want to use, whether we want to include a previous word or not, which coverage function to use, and so on. Further extensions need to directly change the code. In FirstSec, this is more specific than return. It provides many predefined architectures with hyperparameter tuned, really good for prototyping and fast verification. But if you want to do this modification, you either need to use pre-written modules if they are provided, or extend the code by your own. Here in this slide, I would like to talk about one of the most interesting features in return, named layer-wise pre-training. In principle, the idea behind it is that we construct the network over time iteratively. Let's assume we have an encoder with 6 layers of bidirectional LSTM. And then in the first we add the first layer, then we train it for a few iterations, then we add the second one, train it for a while, and add the third one, and so on. It means we iteratively construct the network until the intended architecture. To do so, you can use the keyword pre-train in return and specify the number of repetitions. For example, here I have 5 repetitions for each step. And then you need to customize your own construction algorithm if you want. Here, for example, we have it as a function. We first count how many layers we want to have, and then we iteratively include forward and backward LSTMs into the encoder. The next architecture is transformer. Based on the fact that transformer model is much more complex than the recurrent attention models, I'm not going to show you the entire config in return. Instead, I will go through the most important components in order to build a state-of-the-art transformer architecture. As you may know, we have 3 different inputs to the attention block: key, value, and query. And in the self-attention encoder, key, value, and query are all the same, and the input and output has the same shape of batch size times sequence length times feature dimension. While in the decoder, we have a masked self-attention because we want to avoid seeing the following positions. It's an autoregressive model. What we can do in training, based on the fact that in training we still have the whole sequence, we do the dot product, but in order to avoid flowing this information from the following positions, we set them to -infinity to prevent them from waiting. In return, you can use self-attention class for this purpose. And this layer also works within the recurrent sub layer for decoding. However, in training, it is optimized to work fully parallel and not step by step. The second block is a rather simple block, feed-forward block, and you can use class linear. If you want to have any sort of activation, you can set it via activation. For example, in transformer architecture, we usually use ReLU functions. Other that, you can set it to none for linear projection. Another component is encoder-decoder attention block, or cross-attention between encoder and decoder. Key and values are the encoder outputs, while queries come from the corresponding decoder layer. In return, instead of using self-attention layer, we built cross-attention with more basic layers as listed here. It gives us more freedom. And for pre-processing and post-processing blocks, in return, layer normalization is dedicated as a pre-processing step, while dropout and residual connections are used as post-processing. I will note that the order of these processing as well as how we apply them can be different in different implementations. For example, in FirstSec, we have dropout, residual connection, and layer normalization as post-processing step. However, in FirstSec, you can simply return back to the tensor setup by displaying. The last component is positional encoding. Positional encoding is a crucial feature for machine translation to preserve the order. There is an extension to that named relative positional encoding, and the experimental results show that they generalize better than absolute positional encoding over longer sequences. In return, we have two classes for those encoding, and here you can see a simple example how to use relative positional encoding in your config file in return. The next topic is hybrid NMT. As you may know, transformer model trends faster while they are slower in decoding. Therefore, it would be interesting to combine RNN and transformer architectures, as it has been done in this paper by Chen and Firat. The main idea is to receive information from different channels, and based on their observations, the best setup seems to be transformer encoder and RNN decoder equipped with additional layers. They also provide one architecture named RNMT+, which is deep LSTM networks. And here in this figure, you can see the encoder of this architecture and the corresponding config in return. For example, we have source embedding, then we add dropout, we have forward and backward LSTM, then we concatenate them using copy class. Again, we apply dropout, then we do residual connection between the source embedding and the output of this dropout. And if you want, you can do the final projection. If you want to have this layer 6 times as your encoder, then you can put these lines of code inside a function and then call it n times. How about hybrid NMT in other frameworks? For example, in Sokai NMT, we can specify which type of encoder and decoder we want to use via options. Of course, again, further modification requires a little bit of change. However, in Sokai version 2, they are much more generic than Sokai 1. This is the same case in FERSEC as well. We need to slightly modify the code in transformer.py or LSTM.py modules if required. To conclude, with the generic framework for machine translation and machine learning methods in general, we have more freedom to design our architectures. Thank you.
Hello, my name is André Merboldt, and I will cover the speech recognition part of this tutorial. I will go into details on hybrid HMM training, attention, and transducer models, as well as encoder pre-training. So the goal in automatic speech recognition is to recognize a given speech signal, and we evaluate our models on the error rate, and depending on the application, also in latency and speed. Common models include the hybrid HMM model, CTC, ASG, lattice-free MMI, as well as newer approaches like encoder-decoder attention and transducer approaches. The open source frameworks, which are available on GitHub, for example, are DeepSpeech, ESPNet, Kaldi, Web2Letter. For example, DeepSpeech includes the CTC model and is for production setting, while ESPNet is geared more towards research and includes a lot of different models. And in terms of framework support, so how can researchers benefit from using a framework, especially for ASR, is that it enables fast iteration speed that was already mentioned in the first part. So the framework should be flexible and simple enough. And for example, using custom user configuration or code, so researchers can try out different ideas without touching stable code. And that stable code includes the building blocks, such as encoder, decoders, as well as losses and beam search. Those should be of efficient implementations and high quality code. Important aspects of ASR include the input and target features, as well as the acoustic and language modeling part. We might also have a front end before the encoder, which might include random data augmentation, such as spectral augmentation. And for language modeling, we also have to consider whether to or how to integrate the language model during training or recognition. And this is part of the fusion techniques. And of course, we have dependency between all those aspects. Other aspects include the network size with respect to the parameters. So this is important when we have to decide where we want to deploy our model, on embedded devices or on server applications. We have techniques available such as quantization or teacher-student training to cope with that. Also, we have to think about when we have recurrency in our network. So for example, in LSTMs, we have to think about how it affects our speed and also how to parallelize this model well. When we have streaming ASR, so that means that we have an audio stream coming in and we want to recognize it while the system is running. We might have to perform other features. So for example, we have an BLSTM as an encoder. So we might have to switch to other techniques such as latency controlled BLSTM, because the BLSTM by definition is offline, so it has to consume the whole input sequence. Or we can do frame chunking, or we use unidirectional LSTM. For transformer, there are similar techniques such as local context self-attention or block processing. And also in the decoding part, especially for attention, because in attention we assume that in global soft attention we have to assume that we have access to the whole input sequence. We can switch to hard attention, where we attend only to a few frames. We can use monotonic chunk attention or various other techniques such as CTC synchronous training or triggered attention. And also we have to consider how well the framework supports our production setting. So for the models, we have in the acoustic model, that is the encoder, we might have LSTM stack, transformer or convolutional networks. These all might have variants or combinations. And for the decoder part, which does the sequence modeling, we might have a hybrid HMM or CTC, or some attention-based encoder-decoder model that is, for example, global soft attention, self-attention, such as used in the transformer network. Or we might have a local soft attention, where we only attend to a small window of the input sequence. Or also hard attention variants, such as the previously mentioned mocha or latent attention. Also, there are transducer models, such as recurrent neural aligner or transducer. And we have also a generalization on that. And there might also be a new approach at this interspeech. So the Razor toolkit is the RWTH speech recognition toolkit. And the features relevant for training hybrid HMM models include the hybrid HMM GMM trainer, forced aligner, card estimation, as well as search. And we also have different APIs for different tasks. So for example, the feature extraction module, sequence discriminative training criteria, as well the hybrid HMM model. The training where we can plug in any framework such as TensorFlow or PyTorch, and then to perform the training in Razor. Also, we have the TensorFlow C++ API, where we can load graphs and checkpoints for further training. And of course, much more, but those are the features relevant for training hybrid HMM models. And now to the interface between our framework Return and Razor is that we can use Razor for feature extraction. So, for example, we can load the dataset, including the forced alignment, using this dataset for frameworks cross-entropy training. Or we could use Razor decoding. That is, we use return for acoustic modeling via the Python interface, or we could compile the TensorFlow graph and use it directly. Also, we can use return for language modeling, and then there we compile the TensorFlow graph and use it in first-pass decoding. We can also do second-pass decoding in return directly on the letters. And also it includes sequence discriminative training, where return computes the posteriors and then passes it to Razor, which then calculates the loss and gradient and passes it back to return. Another feature is the extraction of finite state automaton using a pronunciation lexicon on phonemes. So Razor can compute the FSA and then pass it to return, which then performs CTC training using a fast Baum-Wade algorithm, and then can compute the CTC training, full sum training. Another model which is very popular lately, not only lately, it's been around for some time, is the encoder. It's the attention model. So it includes an encoder, which in this example is shown as a BLSTM stack with the time max pooling. So it reduces the input by the factor, for example, 6, and then this encoder output is attended to by the decoder, which runs on the label position, and it receives the label at the previous position, computes the attention, attends to the encoder, and then passes it through the network, and then produces an output distribution. Now the training is fairly simple because we can simply use cross-entropy training. So we minimize our loss, which is the negative log posterior probability, with respect to the model parameters. In recognition, where we don't have the target sequence available, we have to find y such that we maximize the log posterior, and we can do that using beam search, which is then labeled synchronously, and it usually has a rather small beam, which compared to hybrid models such as 12 in our experiments. And we have a fairly straightforward configuration for return for our attention models. Pre-training in ASR is also very important to improve convergence and also final performance. We can grow the encoder and or decoder. We can play around with the learning rate. We can schedule it. We can initialize parameters from a different model. For example, only for the encoder. We could also do curriculum learning, so that easier parts of the training are seen first. And now the question is, how can frameworks support this? For example, for once, we need to have high flexibility so that we can incorporate all those techniques, as well as providing recipes, configurations, or examples for training on specific data sets so that researchers have a good starting point when trying out new ideas. One example of such pre-training scheme is shown here. So again, we have an encoder which is a BLSTM stack. We start with 2 LSTM layers of fairly low dimension. Between those, we have a max pooling layer over the time dimension. The reduction factor is now 6. Then in the first pre-training step, we add regularization with dropout. Then we add another BLSTM. So we have now 3 LSTM layers. We also grow in the width of the network, and we distribute the max pooling layers between those two. So the final time reduction is the same. Then we can add another BLSTM layer, another one, so we grow in depth and also in width. Finally, we add label smoothing as a final step. So that's our final encoder. And that encoder is also used in the transducer model, but we could also use a transformer network or any other encoder. So in the transducer model, as I said, we have an encoder and also a prediction network, which is similar to the decoder in the attention model. It operates on the label position S and receives the last non-blank symbol emission. That output of the encoder and the prediction network is combined in the joint network that we call fast-on-n. It explicitly operates on the alignment position, and then the output is put through a softmax to produce a output label distribution over the vocabulary and the blank symbol. So we have generalized this using fast and slow on n, as well as over the output label topologies on NT, on A, and CTC. The training criteria includes full sum training. So there we marginalize over all possible alignments. We consider all possible alignments with respect to the label topology. Or we could do framework cross-entropy training. That is when we have an alignment fixed, a path through the alignment lattice. And in the recognition part, we perform beam search over the alignment axis. When we have RNA or CTC, that is time synchronously. Another sketch of the transducer model is shown here. So we have basically three different parts: the encoder, the slow RNN, and the fast RNN. And we also have three different time axes: T, S, and U. The T is the encoder time axis, and it is downsampled from the input per the time reduction. S is the label output axis, so that is the actual labels which are emitted. And U is the alignment axis, so that's the fast RNN. It runs over the whole alignment. And in each fast RNN step, it produces an output, which can either be blank or an actual symbol. So fast RNN runs over the alignment axis. Slow RNN is only updated when an actual blank actual symbol is emitted, such as shown here when it's bold. And yeah, as I said, the alignment axis is equal to the encoder axis for time synchronous models. And slow and fast RNN are just names, so it could also be a transformer or convolutional network. And the implementation of the extended transducer in a framework includes our training pipeline. That means we first perform full sum training, then extract some alignment, the best path alignment, and then perform viterbi training. For the full sum training, there exists open source CUDA implementation for TensorFlow and PyTorch. So that means that the framework has to support executing native code. And in the forced alignment step, in the second step, we can either modify the CUDA implementations or write custom backend code. So that means instead of taking the full sum, we exchange the sum with the maximum and then backtrack the best path through the lattice. We then save the alignment to file and then perform cross-entropy training in the last step. We could use the same or bigger model. Actually, we could also initialize the model with the full sum trained one. And because in this case, where we don't have to perform dynamic programming as in the full sum training case, we could use the fast RNN with an internal state, such as LSDM or transformer models. For the recognition part, when implementing this in a framework, we have to implement a custom beam search because the beam search runs over the alignment. So the framework has to be very flexible and also extendable to support this. And yeah, in return, we have all three steps implemented in a configuration file, and I will now go into details on how we implemented this in return. So as usual, we have a model which is defined once, and training and recognition share the same logic. So during training, all layers are moved outside of the loop, so that is efficient implementation. The loss computation, or in the full sum case, as I said, we have to perform dynamic programming, which using the CUDA implementation is still very memory and also computationally expensive. With a fixed path, so cross-entropy training, that is very fast and not so memory expensive in comparison to the full sum computation. During recognition and search, we simply perform the single steps as explained earlier. So fast RNN is updated every frame, slow RNN is updated only for non-blank symbols. Blank symbols are then masked away for the output finally. And now to the slow RNN implementation. So in training, because we have operations running on different time axes, that is especially the alignment axis and the label output axis, we have to synchronize those using a combination of scattering and gathering. You probably know those operations, mask scatter or scatter ND, in PyTorch and TensorFlow. Because then we have the same time axis and then we can perform efficient implementation. So in return, we have implemented this using the mask computation layer, which based on the mask can either perform some computation or it doesn't. So the mask is the previous output emission. which is true if the last output is an actual symbol and false if the last output was blank. Now to the actual implementation, we have a mask computation layer, the mask, and then we also specify the input. And the subnetwork is constructed, so the slow online is constructed using the subnetwork, which first computes an input embedding, which is a linear transformation, and then we have an LSTM, which receives the input embedding, and then simply copy the output from the LSTM. And in recognition, we then in each step make a choice. For the mask, when the mask is true, we update the slow on-end state. If it's false, we copy over the last state. Now, another possibility to model our transducer model is that because we have to produce a label distribution over the extended vocabulary, and that is the vocabulary including the blank symbol. So there we have two different variants. One variant is we call the explicit blank. So first we have a readout layer, which is basically just a max out layer, so linear transformation, and then we reduce the feature dimension. Then one variant, which is very simple, we have a feed forward network based on the readout layer, and then we perform the softmax in the log domain over the vocabulary including the blank. Another variant which adds a little bit of modeling power is the separate emit model. That means we first decide whether we want to emit or not. When the probability that we want to emit is modeled by the sigmoid, which is a feed-forward network based on the fast on-end state, which is shown here. So it's a linear transformation, and then we perform the log sigmoid because we do every computation here in the log domain. And the other decision, when we don't want to update the state, is shown here. So we simply take the negated input, which is shown here. The blank log probability is the log sigmoid of the negated input, which was computed here. Then we compute the softmax over the vocabulary, so that is without the blank symbol, based on the readout layer. That again is a log softmax, and in the final step we can then combine both probabilities. So we have the combination, which is simply a multiplication of the softmax and the probability that we want to emit. So that's label log probability with emission log probability. Multiplication in the log domain is an addition in the linear domain. So or other way around. And now when we have the output log probability, we simply concatenate both log probabilities from the blank and from the label log probability. So that's one example on how one would to change the modeling power of a transducer model.
In this part of the tutorial, we would like to briefly cover the task of language modeling. For those who are new to the field of speech and language processing, a language model estimates the probability of a sequence of words, or in general, a sequence of any token. Therefore, its training requires only monolingual data. It's an unsupervised task, and as a result, we have a lot of data available. In that context, scaling up language models in terms of training large models as well as using a lot of data would play a key role in advancing these models. And some crucial questions come up, like how to scale up. Do we have the software? How about the computational power? Do we really need to adopt the algorithms? As well as how to use and benefit from the available data. Language model can be used in different applications like ASR and MT, although its effectiveness is limited for machine translation compared to the back translation method. It is still an important component in both conventional and end-to-end ASR models. We have plenty of frameworks for language modeling, both count-based and neural models. But in the following slides, I'm going to cover some of the important features in return as an example implementation of machine learning in general. First, what language model expects from a framework? As I said, besides scalability as a major feature, we would like to have easy architecture setup, for example, STM and transformer language models. We want to evaluate our models based on perplexity properly. For example, correctly normalize the scores, per position scores, and so on. Easy integration to ASR experiments, rescoring, re-ranking, various fusion techniques, support of different units, easy sampling for back translation as well as corpus filtering, easy comparison and interpolation with count-based models, speed-up methods, and some other general features. Let's see language models in general. The early models are based on n-gram count-based, which are computed using relative frequency counts equipped with smoothing technique. As neural methods, the standard choice is LSTM RNNs and for many years. And we have many alternatives for LSTM language models like gated convolution, wavenets, FEFO, highway and memory networks. But none of them really replace LSTM until the success of transformer models, which are usually deep. Okay, let's see how we can benefit for language modeling in return. Return basically supports almost all crucial features for language modeling. In terms of data, it supports plain line-based text using LM dataset, as well as conversion to HDF format using HDF dataset, which requires less memory. It supports modern language models with neural networks, both LSTM, self-attention based, and others. Different units like character, subword, words are supported for large vocabulary, and we can benefit from efficiency of softmaxes and used sample softmax or noise contrastive estimation. It is also simple to integrate language model in different tasks like speech, translation, and potentially other NLP tasks. And many more features like training algorithm, batching, and so on. The n-gram count-based models are really fast to train, and they can help the neural language models from 2 points of view. The first one is that they can be used as a reference perplexity without hyperparameter tuning of the neural models. And the second point is that they can be used to detect the domain signal in the text data. Therefore, it would be nice to have an easy comparison and interpolation with count-based models. Return offers one tool for this purpose, and this tool evaluates perplexity with and without context across sentence boundaries and prints token-wise probabilities in the good old SRILM format shown here. And how about network configuration? For example, here you can see an example where we have 2 layers of LSTM for our language model. The first layer is just embedding. We have 2 layers of LSTM. Then we have projection. Here dropout and L2 weight regularizations are optional. If we want to do weight tying, for example, if we want to tie the embedding and softmax matrices, we can use reuse params. What we need to specify from which layer we want to tie it to. For example, here the input and output layers are tied to each other. In order to transpose the matrices, we need to set this flag to true. As default, the cross entropy loss does not report the actual value for perplexity or the exponential loss. Therefore, if we want to have it, we need to activate this flag and set it to true. Another model is a transformer model, which gives large improvements over LSTM language models, as shown by André and Zeyer. For language modeling with transformer architecture, we don't need positional encoding necessarily. Therefore, if we want to have language models, we can simply configure our network similar to MT decoder using provided building blocks. It would consist of self-attention and feed-forward modules equipped by dropout, residual connection, and layer normalization. In order to reduce the hyperparameters, the number of hyperparameters, we can use the same dimensionality across all layers. So, given a trained language model, we want to integrate it in different tasks like speech and translations. One setup is the fusion, which can be write it down via config. The first one is the shallow fusion, which is done only during search, while the other fusion techniques like deep fusion or cold fusion, as well as combining acoustic and language model scores on the probability level, can be used in both training and decoding. To do so, we need to load the language model parameters with the same output vocabulary as the acoustic model. The language model trained by return can be also used for the conventional speech recognition. Return provides a lattice rate scoring tool based on TensorFlow C++ API, which takes HTK standard lattice format as an input. We can also have a tool in our speech framework Zeyer, which takes the language model trained by return and does lattice rate scoring and first pass decoding. So, given a trained language model, we want to do shallow fusion in attention ASR model, as shown here. To do so, we need to do it via the subnetwork layer. Here we define our language model in the subnetwork, and then we load language model parameters using load on init to specify the path to the language model checkpoint. Here a native LSTM operates step by step, and using eval layer we can have a simple implementation of log linear combination to combine the acoustic and language model scores. Here, for example, we have LM scale to weigh the language model score by 0.25. Given the acoustic and language model score, then we can combine them using eval. And we can also have sample softmax and NC as a speed up technique. In return, we have both to ease the softmax, and they are options for our loss. As you can see here, the sampler and the number of samples are hyperparameters to be chosen. If we want to have proper perplexity calculation, we need to set useful softmax to true. These sort of speed up techniques speed up without any performance reduction. That's all for language modeling. The next application to address is the speech-to-text translation, or shortly ST. We have already covered both automatic speech recognition as well as machine translation, and the natural question would be, why not a speech-to-text translation? As a short introduction, a speech-to-text translation refers to the task of translating speech signal to target text. And the traditional way to do that is the cascaded system, where we concatenate the ASR and MT models. In practice, the nearly zero recognition error cannot be expected. Therefore, the ASR errors are propagated to MT model. In addition, in these models, we need to first transcribe an utterance, and then an MT model needs to translate the transcribed sequence. Therefore, this is a two-pass decoding, and we need two models. Leads to more computational complexity. In contrast, we have end-to-end models, which are trainable in an end-to-end fashion. The most promising model is the direct model, where we have no dependence and supervision on the source transcriptions or as an intermediate representation. There are other techniques like transfer learning, multitask learning, and two-stage models, which we are going to cover in this talk. For speech translation, there are some frameworks publicly available, and all of them support both cascaded and direct models. In addition, FirstSec speech-to-text supports online or simultaneous speech translation. What speech translation requires from a framework? Besides the general and important features, as mentioned before, we want to have easy architecture setups to enable different models. Easy integration of ASR and MT models for cascading is an important point. For example, whether the frameworks support plugin to other frameworks like hybrid HMM models, as they are the state-of-the-art models for ASR. Some features like freezing parameters, transfer learning, multitask learning, which speech features we have in the framework: MFCC, LogML, Highbot, model units, subword characters. Do we have data augmentations? Generating syntactic data is possible both on text and speech, knowledge distillation, enabling the usage of pre-segmentation speech frames. Online capability, where we need to handle the latency and to chunk the frames for ASR streaming and so on. In the following slides, I'm going to show how we can use return to do speech translation. Let's dive to the models. The first model is the cascaded model. The standard choice to do cascading is to run ASR and MT separately, and then write the ASR outputs on disk and then read it again as an input to the MT model. But what we can do, if we can have the same vocabulary on the ASR side as well as on the source side of the MT model, then we can load everything on one config and conduct the search at once. What we need to load all MT parameters with optional name like MT underscore prefix here and ASR underscore. Using preload from files, we define a dictionary with two keys. The first key corresponds to file name, the path, the checkpoint, and the second one is prefix. Then we define ASR and MT models in one single network and passing the one-hot vectors using getBeamed layer. One point to be highlighted here is the activation of include end of sentence token, because as a default setting we don't print end of sentence token on the output file, while here we want to pass the one-hot vectors to the second model, therefore we need to include it. So direct model is the first end-to-end approach. It allows joint training of all model components, therefore it solves the error propagation problem. It also removes the need for explicit intermediate representations, I mean transcriptions in between. But similar to other end-to-end models, this is a data-hungry model and we need to have moderate amount of training data to train them. In return, we can simply have direct models, as they are similar to RNN attention and transformer architectures. Metadata set has been designed to combine ASR and MT data wherever it is needed. One technique which has been proven to be helpful for speech translation is transfer learning. The idea behind transfer learning is to transfer knowledge from different tasks like ASR and MT models, which can be trained using a lot of training data. For example, let's assume we have a pre-trained ASR model trained on ASR data and we have a pre-trained MT model using MT data. Then the ASR encoder can be used to initialize the speech translation encoder parameter. Respectively, the MT decoder can be utilized to initialize the speech translation decoder parameters. We can also include an additional layer named an adaptive layer to match the output of pre-trained encoder to the input of pre-trained decoder. Then, given the direct speech translation data, we can do the fine-tuning stage. How it can be done in return? Again, via config file, we using preload from files, we define the path to the checkpoints, prefixes, and we need to activate init for train because we want to do fine-tuning stage. Then we define the ASR encoder and MT decoder in the network configuration and do the fine-tuning stage. If we want to freeze some of the parameters, we can do it via trainable and set it to false. For example, in this example, we don't train the target embeddings anymore because we set it to false. So next is the multitask learning. The idea is that an auxiliary model is a co-trainer to the speech translations. For example, in this figure, on the left hand side we have the ASR task, and on the right hand side we have the speech translation. In this scenario, we have the one-to-many setting where we have a shared encoder, the speech encoder, while we have two independent decoders. One corresponds to transcription and one corresponds to translation. Here, the blue blocks show the transfer learning. As you can see here, in this setting, we can also have transfer learning as well. In return, what we need, we first construct the speech a translation encoder-decoder network, for example here, and then we construct an additional ASR decoder. And whenever the task is not searched during training, we add this additional decoder to the network. We can also combine the losses using loss scale. And in this example, we have lambda and 1 minus lambda. It means we equally weight them using lambda 0.5. Another setting is many-to-one, in which machine translation is a co-trainer to speech translation. Therefore, we have a shared target text decoder, but two independent encoders. One encodes the speech data and one encodes the text. During training, we need to make a decision from which encoder we get the information. Therefore, we need a switch layer to select the encoder. And during inference, we completely ignore the empty encoder. Again, blue blocks show the transfer learning. Here you can see an example in return for many-to-one setup. We construct the direct speech translation network as usual, and then add the text or empty encoder. Then we have a switch layer to select our corresponding encoder, either text or speech. And we need a condition, a Boolean condition, and this comes from our dataset pipeline and indicates from which encoder we have the available data. In the same research direction, we can have two-stage models in which we rely on transcriptions, but we can optimize the models in part through the end-to-end training. As you can see in these figures, we have the ASR models and then another decoder on top of that, the target text decoder. And we pass information, some internal representations to the second decoder. This internal representation can be attention context vector, decoder states, or any other layer. Again, it can be easily set up via config.y. And to conclude this part of the tutorial, I would like to highlight some of the important aspects for speech translation. Basically, almost all ASR features can be used for speech translation. For example, spec augmentation, CTC loss on top of speech encoder, layer-wise pre-training, and so on. Here you can see an example where we construct a speech translation network and add CTC as an additional loss by defining loss to CTC. Only during training. In general, return provides a generic framework and many interfaces to Zeyer, for example, to have hybrid HMM models for ASR, ASR streaming. Therefore, we can have simultaneous speech translation, segmentation of speech frames using conventional alignments, and some other features. It would be nice to have a framework which has a capacity to be integrated to other frameworks.
Now we come to the last part of the applications, text-to-speech. So when we talk about text-to-speech, or more specific neural text-to-speech, we talk about the neural feature model, which converts text into spectrogram representations, and a neural vocoder model, which converts spectrograms into a final waveform. So for both model parts, there exist different architectures. And for each of those architectures, you can find a lot of, let's say, non-official repositories in GitHub, but there's no real unified framework where you could, or where you already have implemented all of these different models. So an exception is ESP.NET, and also to some extent the Open Sequence to Sequence, as they provide some of the here listed feature models, and we hope that in the future also Return will be able to provide implementations for most of these feature models and vocoder models. So the architecture we choose to present here is Tacotron 2, as this was the most straightforward one to implement. So Tacotron 2 is based on simple encoder-decoder architecture with LSTMs, and the difference to the previously presented architectures in MT and ASR, we have here a regression task. So we have log_my feature outputs, and we need an explicit stop token to mark the sequence end. Also here we have convolutional postnet, which applies a non-autoregressive filtering on the predicted spectrograms from the decoder. So while it was not too difficult to implement Tacotron 2 in Return, as most of the modules are also found in MT and ASR, we had to add some changes. So the first function that was not covered already in ASR and MT were, for example, the zonod LSTM implementation, change for the local sensitive attention, to add the explicit stop token instead of stopping via target labels, and that the decoder might operate on merged frames. Also, if we want to do feature extensions for Tacotron 2, there are a lot of monotonic attention variants that also need to be considered. So the first example we want to give here is the native support for windowing. So what we mean by this is that the framework should be capable of handling windowing in an easy and flexible fashion. So what we can do in Return is that we use a window layer to split the features for the decoder target into, for example, groups of 2, here by setting the window size of 2 and the stride of 2, and then merging the resulting window axes into the features, so that we now can predict 2 features at a time as output for the decoder. Because we want to run the postnet on the single feature frames, we need to undo this merging. So what we can do here is that we first split the dimensions again into the window axis and the regular feature axis, and then merging the window axis back into the time axis. So this gives good control of the windowing behavior, that we can predict an arbitrary number of frames per decoder step, but still can revert the process and operate on the single frames in the postnet. While we can add overlapping windows by using the window layers, so far Return is lacking a layer to basically add the overlapping windows back into one sequence, so this would be something to be implemented for the future. Another example we want to give here is the location-sensitive attention. So while this is similar to the attention methods we already have, for example, in ASR, here we added some specific padding. So we choose to pad the left side or the starting side of the previous attention weights with 1, and the right side or after the end with zeros. But then we could just apply the regular convolution, do a linear transformation, and add this to the attention energy. So it is quite simple with this style to implement different attention functions. But this might not be the case for all attention methods. So for example, a more complicated issue is the dynamic convolution feedback, because here the convolutional filters are computed by the output of the decoder. So the convolutional filters are computed depending on the state. And this means that the filters are independent for each batch position. So the function that is capable of handling independent convolutional filters is, for example, the TensorFlow.nn.depthwise_convolution layer, which would be needed for the correct filter computation. And because we do not have an implemented layer yet in Return, to implement this, custom TensorFlow code would be needed. And this means that here we have a lack in flexibility. So here we would need additional overhead to create the custom layer in our config file and then implement this dynamic convolution feedback. Then we wanted to compare how complicated this would be to do in ESP.NET. because ESP.NET offers a well-documented class, for example, for the location-sensitive attention called utlog, and it even provides additional features such as adding window constraints, softmax scaling, and the encoder context precomputation. But we also found some downsides here. So all of the attention mechanisms that are available in ESP.NET are basically part of their own code block. So this means that there is a lot of redundant code with other attentions, as for each attention mechanism, again, we have the implementation for creating the decoder and encoder transformations and applying the softmax, for example. Also, here we would need some more complicated code changes, for example, to change between the sum feedback and only using the previous position. And it's difficult to combine the different types of attention, as each attention is implemented in their own class. In return, this is a little bit easier because, for example, switching between the accumulated weights and the previous weights is just changing one element of the from attribute. Also, we have a very simple method for combining different feedback types, as we can just combine them in the combined layer. And for example, for the window constraints, we have available parameters in our softmax over spatial layer. But as we have seen before, for example, for the dynamic convolution attention or also some monotonic implementations, we might require an EVA layer for very specific constraints. Another aspect of text-to-speech is how to handle multi-speaker. So the example we choose here is the global style token embedding. The global style token embedding uses a reference encoder on the target audio sequence to feed an attention mechanism that is selecting a mixture of trained, let's say, feature banks. And the mixture of these feature banks is used to form a style embedding. So this method is unsupervised. So the TTS system uses the input audio sequence to extract the features required for reproducing the speaker style, the prosody, or other characteristics of the audio signal. If you want to synthesize new speech, we can either use the reference encoder and feed any audio sequence where we want to match our characteristics, or we can provide fixed style embeddings or the fixed mixture weights. So to implement the reference encoder, which is based on convolutions and an LSTM, we do not need any specific new layers in return. But for example, for getting the final state to feed in the attention, we can use either a reduce mean layer, where we then take the mean over the time masked LSTM states, or we can just use the last hidden state of the LSTM. So this kind of layers need to exist to implement the global style tokens. Also, we need variable layer, where we can define how many tokens we have and what is the dimension of the tokens. And in return, we also need an additional reinterpret data layer, where we define which axis is used to apply the attention mechanism on. So the benefit of having this type of layer definitions is that we can add the resulting speaker embedding at any point of the network. So we just can extend the from parameter to add the style embeddings to the encoder, the decoder, or the postnets, or wherever we want. Also, we can just dump the speaker embeddings into an HDF file at any time. So during training, during decoding, and whenever we compute something. And when we run the decoding, we can just replace the full reference encoder and just use the HDF inputs to feed in some pre-computed style embeddings. The last aspect is the vocoder integration. So here we choose the parallel waveguide vocoder as an example, because there's a repository that supports 3 different architectures. And what return needs to do here, or in a general framework needs to do here, is that you can run ground truth aligned decoding, so that you run your decoding by still feeding the actual target labels, so that the audio and the spectrogram is synchronous. And we can just do by turning on the return eval mode and dumping this with the HDF dump layer. And then we just need to convert these HDF outputs in something that can be read into the parallel waveguide implementation. In general applications for decoding, we want to have also our text processing, the feature generation, and the vocoder all in one process. So for example, if we write a server application that takes text and gives back the audio. So for this you would need, for example, numbers to word conversion, or a grapheme to phoneme model, as we gave here sequitur as an example. And what you can do with return is that you can just call the graph loading and the forward step for decoding from any arbitrary Python script, because it also provides a Python API and not only the run command to run on the fixed configuration file. And so it's quite easy to combine the text processing, return, and PyTorch applications such as the parallel waveguide decoder into a single software. So now we come to the conclusion of the second part of the tutorial. So in the second part we have seen that each application has its own needs with respect to the data processing, the model architectures, and decoding methods. But we know that all applications have the same needs with respect to the flexible network design. For example, we've seen a lot of different attention extensions. And of course, each application has the need for a high training speed and a high decoding speed. So every application can, of course, use the automatic optimization we've seen in the first part of the tutorial. And of course, having an understandable API for designing all the applications is nice. So we think that given the right concepts, that a framework can be capable of handling arbitrary tasks and architectures without too many limitations. And that also given the right concepts, a framework should not lose any convenience over flexibility. So that even when you design a framework to be flexible, you can still get the same convenience as software that is targeted to a specific task. So what you should take home from this tutorial is that there are some nice concepts, as for example the tensor management concept that we presented in the form of the data object, which is really useful for increased flexibility and simplicity when designing networks. And also concepts like maintaining your stochastic variables in a defined model, which really helps implementing some architectures that are non-standard encoder-decoder, for example, the transducer architecture. Also, when writing your implementation, it would be nice to consider writing the most used operations in native code, for example in CUDA, as this was really beneficial in our framework return, but is also used heavily in Lingvo or Rough2Letter++. Another thing is that for a framework it is beneficial to provide generic interfaces to external applications. So in our case this was Razor, but there are also many frameworks that have good interfaces to communicate with the open source Kaldi software. And overall, it is nice for a framework to provide documented task examples, as this is done in ESP.NET and Open Sequence to Sequence, as this really introduced the entry barrier for using a framework. And this is still a problem in return, that we don't have too many of those documented tasks. Also, it is important to include additional tools, so that you not only can build your model in the framework, but also do evaluation and analysis, or maybe do plots of attention weights. And you should consider that you aim for flexibility before your codebase gets too task specific. So in return, we had the problem that in the beginning it was too much focused to ASR only, and then it gets more difficult to make it more flexible in the end. So yes, thank you for your attention watching this tutorial, and now we come to the question and answer session.